All right, Carla.
All right, great. I will try to stand the appropriate distance from you. So I'm Carla. I am a principal research at SDE in Microsoft Gray Systems Lab. Today I will talk to you about vertically autoscaling with Cassandra, and this is collaboration with my coworker Anna Pavlenko, the whole Gray Systems Lab team, and Gerben Eichberger at Microsoft. So first, a little bit about me. I am from the research side, so not production, no pager duty, and I work in Gray Systems Lab, which is kind of a mix of a whole bunch of different databases, so SQL Server, Postgres, Spark, Cassandra, you name it, kind of all thrown together with a bunch of researchers, with a mix of ML researchers, infrastructure researchers, AI researchers, that sort of mix. Before coming to Microsoft, I completed my PhD 10 years ago, and I worked as a researcher in the telco space, doing autoscaling there at Intel Labs. And my current research is I focus on optimizing cloud infrastructure for database and machine learning workloads from a general perspective. So I want to make it very clear that I am just learning about Cassandra, and I'm excited to learn more about Cassandra from all of you in these talks. But I'm hopeful that some of the techniques that I mentioned today are useful to you because it's generally applicable across a lot of areas. So how this whole got started with this vertical autoscaling, our team was tasked with autoscaling these monolithic databases running on Kubernetes. So we had these deployments of one primary and two secondaries, very fixed, very legacy architecture, where we can't scale out to more instances, and we need to figure out how to optimize our resources. So one of the things we started looking at was usage and use case and across that area. And one of the things that was blaringly obvious is that many users were over-provisioned in terms of CPU allocation, often by a lot. And so this graph, I have this blue line at the bottom. This is actual CPU usage, the axis on the left. And then at the top is the CPU limit setting. So here the user was using Kubernetes. They set their CPU limit to 14. We're billing a number of CPUs per hour. And so you can see how all of these resources are being wasted. So that kind of began our vertical autoscaling journey. Looking into Cassandra, I know that Cassandra is famous for its linear scaling. You just add more nodes, super easy, bang, you're done, right? But I'm told that bringing up a new node for horizontal scaling, this involves data movement, and this can take a lot of time. Whereas with vertical scaling, you don't have to worry about data movement. And additionally, this is just one more way that you can right-size. So it's an additional tool in your toolbox. And I know that there's many ways to run Cassandra. You can run it on bare metal, on VMs, containers, Kubernetes, Cassandra. But the ideas that I'm going to talk about today are generally applicable across all infrastructure choices. And the thing that I'm really excited about is, depending on your choice or your setup, we can often scale the number of CPU or the number of cores in place without a restart, so we can seamlessly right-size without the users even noticing that we've made a change. So here's a picture just in case when I'm saying vertical scaling, it's not straightforward. If you don't understand this part, it will make the rest of the talk confusing. So I'm beating this home. So here I have a database that's running as a replicated set of 3 pods. Each of them have n cores each. And Kubernetes, as you know, famous for the horizontal scale out. But in our case, we're going to be just resizing the cores in place. So here we're switching from 3 cores to 4. And when we talk about autoscaling, what I mean is, so here we have some sort of a controller. Again, staying agnostic, this could be Kubernetes, it could be any bespoke program meant to make changes as needed. We have our application, which in this case today is Cassandra. And we have our metrics server, a bunch of metrics. And then one of the main points I'm going to talk about today is pluggable recommender algorithms. So how we scale and by how much. And writes these decisions to file. This could be any service. And then we need some sort of a check to make sure, are we healthy? Do we have resources to do the scaling? And when we do, take the decision and trigger the action. So my little from 4 down to 3, for example. So today I will be talking about the mechanism of vertically scaling in place and what that might mean for Cassandra performance. And then we did a little bit of work in terms of policy, our algorithm for balancing a price performance trade-off in terms of how much to scale and when. And then we have a bunch of code that we just released that has made our whole vertical autoscaling journey so much easier, a simulator that I'm going to show you how you can use to try this out on your own. So first, focusing on this mechanism of scaling in place. I think I know most of you know about rolling restarts. I think that's the most common way when you do any sort of upgrade or change in a distributed system is you'll update one of these nodes and then you'll update the next node and then so on until you updated all of your nodes to the new cores. This is the way that we were doing this in production today for one of our databases. But we found that even though we have this beautiful rolling update, it was kind of a disaster for performance. Especially with databases, you want to be extra sure that you're not violating any of your HA guarantees. And so this database, not Cassandra, but this example, we showed the rolling restart process took like 15 minutes so that even when your policy is saying, okay, I'm getting throttled here, my red limit line's too low, my blue line is clearly, like my CPU is getting throttled, it's saying scale up, but it can't because the rolling restart takes too long, and then we end up with a lot worse experience for the users. So if we can do this without restarts and in place, then we can scale much more frequently and without as much impact. So some of you might have played around with this with Docker. You can easily, if you're using CPU quota or some other method of constraining the amount of CPUs on your running Docker container, you can just update the CPUs. This will just change the C groups on the container, and that will change the number of CPUs allocated to that process. And then a really cool feature that I'm excited about, I've blogged about this in Kubernetes, there's an alpha feature that allows you to do this in-place pod vertical scaling there as well. So you just flip the feature flag on, and then you can do your updates in place. But at this point, I started to shop this idea around, and the first concern people are saying is, that's great, you can change resources underneath the running process. What does that do to the running process? Well, so the first database that we looked at was SQL Server, and so we asked this question, what happens? So we spun up a three replica SQL cluster on Linux on Kubernetes with 32, the Kubernetes nodes each have 32 cores. And we did this test where we started, we set the limit for the pod to 2, and then 4, and then 6, kind of on up to 24, and wanted to see what the average throughput looked like over this change. So we did 2 tests, one just with scaling, like I just said, and then a second test where we were coordinating and telling SQL, hey, we're about to change some resources on you, heads up. This graph is kind of an eye chart. I was lazy and copied the slide whole rather than simplifying it for you, sorry. But the top graph is when we do the scaling only and don't tell SQL we're making changes. So the number of transactions per second was 3,960. So we're starting with 2 cores. We're telling SQL Server you have 32 cores, but we're only giving it 2. Then we're telling it it thinks it has 32 cores, it gets 4, and so on. And in the bottom graph, there's like this affinity setting where you can kind of give it a hint to have, say, less threads or less resources, less lock weights. And what we found when we gave it a hint is that we got, especially in the 2, 4, and 6 core case, like a 30% boost. So overall, the throughput of transactions per second was 4,100. So we thought, okay, wow, that's pretty big, especially since the majority of our workloads are often scaled down to a small amount. So this is critical. So bringing this back to Cassandra, what does this look like? So here we have a real user trace. It's a 6-node cluster graphed here. And we thought, okay, clearly this is the quintessential case for autoscaling. It's even like predictable autoscaling. There's a clear pattern, days, nights. Many of you have seen this, but this is a particularly beautiful example. So thought, okay, this is easy. But what is the impact? What happens to all the locks, buffers, threads if we tell Cassandra it has 32 cores, but then we only give it 12? So being a researcher, we did some experiments. We tried a bunch of different scenarios. So first, we would start Cassandra in a way that it thought it had 4 cores and we gave it 4 cores, or it thought it had 16 cores and we gave it 4 cores, the same with 8. And it was pleasantly boring. We ran a bunch of performance tests. We didn't see anything strange in like any of the performance counters, the throughput, anything like that. So then we got a little bit more extreme, and we got a 96 core VM, and then gave it only 8 cores. So it thought it had 96 cores, we gave it 8. The 8 cores was enough to handle the workload, but we still didn't see any extreme performance difference. More investigation is needed, but it's like initially exciting, promising results. So digging in a little bit more into what's going on. So there's Java's public int available processors, and we've seen other applications where they pull this explicitly. I didn't see in Cassandra while that was happening, it checks it at startup. So because of it only pulled once, which is a reasonable assumption, it doesn't see the new cores. It doesn't get updated with the new amount. So one important thing that we learned, in order to use new cores, we have to start it at a high number so that the JVM can see all the cores. So for example, I would need at startup to say, hey, you have 96 cores, and then I can scale it down to 8. The reverse doesn't work. So I can't start it and tell Cassandra you have 8 cores, then give it 32, it will still be locked at 8. We saw some additional JVM weirdness. We're still kind of digging into that. If anyone's interested in this, I'd be happy to hear your thoughts and learn more about that. And at this point, usually the database guys are like, what about memory? Like, you can scale CPUs in place all day, but memory. So memory is really hard. Resizing memory without a restart is very challenging, and that is regardless of platform. So Python, C, Java, all of that, it's a challenging problem. So if you need to resize your memory, at least for now, you need to require application, like an application change, like we're playing with, oh, can we rewrite Postgres? Can we dig into the internals of Cassandra? For now, we are focusing on CPUs. All right, so next is now that we have this ability, how do we decide when to use it? There's a whole paper on this if you want to dig into the details. We presented this at SIGMOD in Chile in June. And a lot of times people ask, why did you write this whole separate paper? What's the point of this? Don't you know there's Kubernetes vertical? Well, that's a fair question. There's, many of you may be familiar with horizontal pod autoscaler. There's also vertical pod autoscaler. But we found it didn't really work for our database workloads for the most part. It's very much tailored to scheduling, effectively scheduling your resources on a cluster, rather than looking at performance or other such aspects. For example, for billing, we scale only at whole cores. It just makes it easier for that system. And we have the Kubernetes limits equaling to requests. For those of you not familiar with Kubernetes, this is just very loosely a guaranteed and burstable CPU class. We set them equal to optimize the performance that the customer expects. And that kind of broke the built-in tool. So on the left is the performance that we saw with the default algorithm, where it scales once. So you see the limit line scaled up once correctly, but it kind of never took advantage of the cyclical patterns we were seeing. And then the algorithm that we wrote called Casper, that I'll talk about in a minute, is able to adapt this. So this is the goal on the right. And in order to do this, we need to have both a reactive portion and a proactive portion. So as you know, database workloads can be very unpredictable. There can be a huge burst, there might be a compaction, there could be a lot of stuff that will cause us to need to be able to react quickly. But then if we have a beautiful sinusoid usage graph, we want to take advantage of looking ahead of the curve as well. So for the reactive approach, we have an existing work published in VLDB 2022 about right-sizing the SQL Server skew, meaning number of cores and memory offline. And so we just kind of adapted that and used that to look at this price performance curve of monitoring this change in slope of the usage over time. So we take a window of the CPU usage, perform a logarithmic, some computations on that, and then based on that decide when and how much to scale by. So just kind of roughly, this also allows people to specify, I would like it to be a little bit more cost effective versus I would like it to be a bit more performant. I'll skip the details for the sake of time, but they're all there in extensive, exhausting detail in the paper. And okay, and then the other half is proactive. There's so much work in the proactive scaling space that we knew that we couldn't make an individual, like, unique contribution just because this is such a deeply researched area. So we looked at a bunch of existing products that were off the shelf. We tried a bunch of different algorithms, and we just went with the most simple one, like a naive time series where you look in 24 hours ago, where was I at? That's where I'm probably at now. And in 24 hours exactly, I might be in the same spot. So, and we also designed it to be as pluggable as possible so that you could swap out to something fancier if you need to. So here is a 4-day cycle of the CPU usage graph. And you can see at the very beginning of each of the blue spikes, there's a little bit of throttling where the red limit line doesn't get popped up quick enough. And on the right, we can see that the top red curve has a bit of a gap, meaning that we had no throttling because we were able to throttle up predictively. And no surprise, on the 4th day, it starts to scale up again, but maybe it's the weekend or maybe the database died. No load comes, and then it's going to start scaling the limit back down. So to build this algorithm, we added one parameter, and then we added another parameter, and then we added a few more. So it got a little complicated. Here's just some of our, like, how much slack do I want, does the user want? How much do I want to max autoscale up and down? How frequently? How much historical data? What is the optimal balance between reactive and proactive? How frequently? So these are the things we looked at. And that was exciting, but also at this point, I was panicking because we had a paper deadline, we had a very complicated algorithm, we had 20 plus parameters. It was beautiful, but actually testing the thing was complicated. We had about 37-day-long experiments to run. We were replaying recorded traces on a live cluster. So 7 days minimum for each, but then we only had 3 functioning Kubernetes clusters due to resources. Researchers are always underfunded, and then we had only 10 days to get it all done. So this is where what I'm most excited to share with you comes into place. We built this vertical autoscaling simulator called VASM. So VASM is able to replicate the common components found in an autoscaler. So all of the different scaling up, like the different replicating the actual features of the cluster, the cores, and the resources. And it's able to replay a pre-recorded CPU trace, and in addition, estimate what it will look like in the future. And in addition to all of that, handle all of these parameters, able to tune all of the parameters in a way that allows you to see, if I make this change, what does it look like, without having to wait 7 days to find out. So to get this to work, you need 3 things. You need the CPU data. So here I have a timestamp and the actual CPU, so like 7.2, CPUs are being used 7.04. And then I need my autoscaling algorithm. This can be basically, think of it as a data frame in of timestamps and CPU usage, and you have to output some sort of a decision. And then on the right, you have some sort of parameters that you're going to tune. So for example, in this very simple algorithm, I don't think you can see it in the back, but in general, this is a simple algorithm that is going to, say, for example, add a certain amount of buffer to the number of cores that you see. And when it comes to tuning parameters, we want to find the ideal balance between slack, which is the resources wasted, and insufficient CPU, which is throttling. So we have this beautiful Pareto curve. These red X's are just kind of different parameter combinations. So each one of the dots on this graph is a different set of algorithm parameter inputs to my autoscaling algorithm. And depending on if you care more about minimizing slack versus minimizing throttling, cost savings versus performance, that you can pick different points on the curve. All right, so now to the exciting part, demo. Oh, wait, I have a QR code. Yes, for those of you that want to play along, there is, or you can just go to github.com/Microsoft/VASM. It's pretty easy, but QR code for those that are interested. Hope that was enough time. Oops. Maximizing the as well. Okay, so here is our GitHub. If you go to the examples folder and then go to the notebook, there's a pretty, there's a walkthrough of all the different things, all of the features and capabilities that we can do. Bigger. But as I mentioned, you basically need to have your, you need your three things that are on the slide. Back to the slide real quick, so it makes sense. You need to have your CPU data, your autoscaling algorithm, and the parameters. So here we have our pre-recorded CPU data, and I'll show you a demo with Cassandra in just a second. And then you need to have an autoscaling algorithm. And we provide a dummy one here. I'll show it. For example, this is very simple. You right now this is all in Python, so I can feel the hatred coming at me right now. We are working on making it so that it is language neutral, so that you can write it in your own language. But for this very simple algorithm for this demo, we take a smooth max of the CPU data over time. So if I look at 10 timestamps, I'll do some smoothing, and then I'll add a simple buffer to it, for example. So that would be my new scaling target. And then parameters ahoy, anything with machine learning or any sort of heuristic algorithm is going to be parameters for days. So you can have your algorithm specific parameters, and then to make it as realistic as possible, we simulate lots of different stuff, such as the min and max CPU limit on the cluster, how long it takes your system to actually do the scaling, and then the prediction config. Do you want to look ahead? How far do you want to look ahead? What forecasting model do you want to use? And so that all goes into this window, and that's going to get fed to your algorithm. And then from there, you can, it'll actually execute it. So the rest of the notebook just shows doing a single simulation, but I'll switch to, I built one for Cassandra. It lives in this branch. Okay. So I wrote a lot, as researchers do, I'm sorry. So in this very simple example, we're going to just have two Docker containers with Cassandra. This is not, obviously not a real cluster. But I wanted it to be something that you could just spin up on maybe your laptop or a small VM and try out. So we're just going to make like a small two-node Cassandra setup using Docker. And then I'll be working with this NoSQL bench tool. I know there's a ton of options to generate load. This is just one that we found worked for us. And so it shows you how to download that. And so the first thing we need to do in testing out the simulator is we need to get a CPU trace. And so this shows you how to, I guess, yes, start the benchmark and then start collecting the metrics. So we just have a simple script that will pull down, that will read the CPU usage off of your Docker containers. Because there are multiple of them, it will take an average of those and then ship them into like some sort of an aggregator. You might want to monitor them separately, just come depending on what your use case is and what's important to you. Start the benchmark load. This will start generating the files, and then so it'll start running. A bunch of like the code will start coming live, and then now we've done our initial recording. So this is just basically workload and getting the logs. We haven't done anything yet with autoscaling. We haven't done anything with algorithm. What we've done is we've generated a CPU trace. For those of you that have live clusters, you can just pull the timestamp and CPU off your live cluster and use that data. But this helps for those that want to just test it out real quick. So next, we need to try the autoscaling algorithm itself. So as I mentioned, I work with like a simple one where we're just going to add 2 cores as a buffer on top of a moving average. And we'll say, because we're going to do in-place scaling, we'll only wait 2 minutes after doing an update. This has been kind of fun because now that we can do the in-place updates, your recovery time is 0 because it just scales up and down. But obviously that can be very bad because then you can end up with thrashing the system scaling wildly in terms of limit, and that doesn't really give you enough time to make use of the resources you freed up. So this is one parameter that we look at. How much data to feed into the algorithm, how long to wait between checking the recommendation, max limits. All right. So there's also a front end. with Streamlit. Let's see if it started. Yes, okay. So here is the front end of the demo. Let me make this a little larger. I pre-recorded and uploaded in GitHub an actual CPU trace, so it's easier for you to try out. But this shows, if I want to visualize the workload, this shows a graph. So this is a very simple 40-minute trace. It goes between, starts at 3 cores up to 5, kind of dips down to 1. So this is an example test load. Nothing cyclical, nothing pretty, just a short 40 minutes of data. So, and then here is here's our parameters. So we're starting at, we'll add a buffer at 2. So we want to add a 2-core buffer to all of our resources. So here's the line, the limit line that we're setting, either Kubernetes or Docker or whatever. And you can see that, okay, in this simulation, it's pretty obviously around 2-ish cores of buffer. Then you think, okay, well, what if I try 1? Like, what happens if I change my parameter there? And for 40 minutes of data, we probably just rerun it, but in a 7-day or 30-day performance trace, that's obviously not practical. So this is where it's very nice. And we say, oh, okay, well, here in this, we actually have a couple of points where we get throttled. So that's not good. Maybe I'll try 1.5. So you can just kind of play with it and see. Now it looks pretty good. But with one parameter, I can easily just make some changes real quick. This is obviously not efficient. So we have this ability to do tuning. So in this tuning tab, similarly, we can try a bunch of different parameters. So say for my add-in parameter, I want to all at once try 1, 1.5, and 1, 1.5, and 2. Maybe I ran this before. And then another parameter that we find makes a lot of difference is the window size. So how much data to look at. If you have a lot of crazy stuff going on, making your window too big can make your algorithm perform strangely. But if you make your algorithm too small, then you can't really see ahead and really understand the broader picture. So that's another thing that's very challenging to get right when auto-tuning. So for this short trace, normally a window would be like 20 minutes, 40 minutes, an hour. Since we have only 40 minutes of data, I'm going to try 1, 3, and 5. And this is going to try all of the parameter combinations. So here I have 3 at the top and 3 here. So 3 times 3, it's going to try 9 different possible values. It's running. Pretty soon it outputs a table with how much slack and how much insufficient CPU for some of the values. And then it gives us a graph of where these would place. So the slack axis does not start at 0, so it kind of looks a little off, but it generates a graph. These folder names are randomly generated numbers, and it puts in bold the biggest number, the optimal parameter combination. So it says the winning combination, meaning the least slack and least insufficient CPU, is window with size 3 and buffer of size 1. So we tried this with our 20 parameter algorithm, like up to 40 or 50,000 combinations over 3 or 4 weeks of data, which really helps us hone in on the correct amount of the correct parameters much more quickly. Yeah, so that's the basics of the simulator. I also have a video. I watched the gentleman do a live demo this morning, very brave. After that, I recorded the video. So I wanted to thank you for that. I wanted to show, in addition to the simulator, which I'm very excited about, being able to do a vertical resize in place was such a game changer for us. I know that it looks simple. There's nothing, what you see is that nothing happens, and that's beautiful. Because usually when you do a resize, it's like the system kind of chugs along, the nodes roll, and the update happens. So this is just a video of doing of me force triggering a live update. Okay, and it has sound. So okay, ready to go.
For this demo, we'll have 3 windows: the polling metrics window, the benchmark window, and the algorithm and scalar window. You can see here that we set the initial CPU limits for the containers to 5 CPUs. And here we are running the benchmark load. Now we'll show the Docker stats showing that each container has around 2.7 CPUs being used. For this demo, we intentionally started the full metrics a little early so they have a low CPU reading at the start. This triggers a throttling event so that we can understand how scaling down and back up works. So we scaled from 5 cores down to 2 because the load was too light during ramp up. Now you can see the CPU is being throttled to 2 cores. Next, we can see in the benchmark window how the queue is building up a lot, but what we need to do is correct this. And we can see in the window, waiting for the scale up event, that we go from 2 cores back up to 4. And now we can see the CPU jumps back to 2.7, and we can see the queue starting to decrease.
All right, so that's just an example of how quickly that now that you can do the in-place vertical scaling, you can right-size your cluster. And I think that was pretty much it. Yeah, I have everything that I mentioned today is on in our GitHub. Pretty much everything I talked about is in the examples folder, so it should be pretty straightforward to find. And yeah, and also there's several of our papers that are like kind of the research behind this links there as well. And that's all. So thank you very much for listening.
Thank you very much for this presentation. Deep respect for the great systems lab and for everyone carrying on doing great work at Microsoft. Some of your colleagues have also been super helpful to us in the Accord project. Were there any Cassandra specific problems that you ran into implementing rapid vertical autoscaling, or anything that we could make better? The databases you tested?
Yes, I think that's a great question. Thank you so much. We started out with these monolithic databases where there's one primary and 2 secondaries. And so that our traffic pattern was very much like the primary was the writable primary, and then we had 2 read-only secondaries. And so everything was centered around like the king of the hill or whatever. When we brought in Cassandra, we had 6 or more, 20 or a lot of nodes to deal with. And at first we were taking kind of a blind average of the CPU usage, or just kind of like going in with like, we'll just average these and not look. Every now and then, for most clusters are well balanced, and so all of the CPU utilization is very similar. But there's cases where, and like the Cassandra folks know more about this than me, when something gets kind of a little off, and a few of the nodes are burning hot, and then the other nodes are kind of slacking. And so when we were doing the average there, then that obviously skewed things. We were toying with, could we vertically scale and have the hot nodes with a larger number of CPU and the cold nodes with less CPU? That just seemed very ugly, and a lot of the Cassandra people I talked to were horrified that I mentioned that. So I think that was the most interesting, was like having the balancer element there.
Thank you.
Thanks.
So you work with a lot of databases. Can you comment on how impressed you were with Cassandra?
It was, I love how quickly I could find answers online. I love how fast it was to set up. It was easy to load. There was lots of great tooling around it. It was a great experience. I am serious, yes. And I'm not allowed to trash any of our databases. You can just know my thoughts.
Okay, so during that algorithm, you are setting the CPU limits on Kubernetes. How about the request parameter?
Right. So that is where it got a little, let's see, I have a slide somewhere. That's a great question. We set the limits equal to requests in, let's see.
Yes, so, but after changing the limits, it's also set up to the equal number.
Yeah, we set them equal to each other because we found that.
But each time, even after scale up and scale down the limit?
Yes. I don't know why the slide's not going. Well, we're frozen. Yes, we set them, like, we continually kept them equal because we found that if the customer is paying by the limit and then the request is lower and it's not able to fulfill the limit, then they're kind of getting shortchanged. So we just keep them equal at all times.
Okay, I mean that, but for example, on the Kubernetes, when we have, for example, limits set up on 8 CPUs and we have machines which contain, I don't know, 10 CPUs, and then we are switch that limits, that request to, for example, 12, we have to go to another machine because there is no enough CPUs.
Yes,
So
definitely.
we have to move to another, and that will end up that we cannot do that fast way because we have to switch to other worker.
Yes, you make a really good point. When the machine does not have enough resources, then you have to do it the rolling restart way. So in a lot of the cloud infrastructure that we run, we'll have like these giant VMs and slightly smaller pods, but that's not always the case for some of the larger customers. Yeah. In the back?
A lot of the forecasting you've done is based on the seasonality of the year. Curious if you have any data on not so seasonal workload patterns. If you've experimented with it.
Yeah, yes. I think that this is where the having the reactive portion is so critical. So if the seasonality period it changes for like holidays or anything like that, and it's important that we're able to take over reactively as quick as possible. And then also just it's shocking how many storms there are in the cloud. So like sometimes for whatever reason, like if there's a throttling event or like the capacity just seems off and you have to be able to react quickly. So we found that the seasonality works most of the time, but a strictly seasonal algorithm is not going to work for in most cases. All right, well, thank you so much. I appreciate it.